Travis and I are teaming up with meteorologist Tom Bird to learn how to interpret the weather like pros. From launching a balloon that gathers real-time data to understanding how pilots can use radar and forecasts, we're getting the inside scoop on reading the skies. Stick around. This forecast is one you don't want to miss.
Will you welcome my subscribers to come in?
Travis's subscribers or yours?
No, them.
Have all your subscribers come in.
Okay.
I think we got to get first, before we can go any further.
Yeah. I mean, it's not every day everything gets to go your way. I mean, we're at the Santa Teresa National Weather Station.
Yes.
I wonder how big of an area they're tracking the weather from here.
I think we're about to find out.
Hi, how are you?
Right here, Tom Bird, National Weather Service meteorologist, right, in the El Paso area National Weather Service. And right here with me is Katie Slusher.
Is your family responsible for the slushies that we find in Cassie?
I'd rather call her Katie Flusher instead of Slusher.
Oh.
This guy.
That's what we do.
Ooh.
This is the balloon that we will be releasing, right? Attached to that balloon is what Katie has in her hand. That's called a radiosonde. And that's the instrument that sends data down to the surface as it's going up. It climbs 1,000 feet per minute.
Wow.
For about an hour and a half. It gets to 100,000 feet above the Earth's surface. The whole time it's doing that, it's sending data back down to a computer here in our office, and it's telling us what the temperature is, what the moisture content is, what the pressure is, and what the wind is. And then it has a GPS. It will track this, and it can do the math and determine how fast and what direction it's moving to get wind speed.
Wow.
So all that from this. And so we release this instrument twice a day, 12 hours apart, and we do this all across the country at the same time. As this is moving away from the surface here, it's moving away from the surface in Amarillo, New York, California, England. So right now we're releasing today at 4 o'clock. In Houston, they're releasing it, but it's 5 p.m. there. In New York, it's 6 p.m., so that's their release time. In California, it's 3 p.m.
Synced up.
In England, it's midnight, but we all release at the same time.
Wow. Interesting.
So it gives us a snapshot.
We're going to be late. They're expecting us right now.
Yeah.
How much does one of these things cost?
I'm not sure what it cost. Yeah. In the scheme of everything else that we do, it's a pretty low cost. This is the entry point of all the data that goes into our modeling.
Wow.
So there's no forecast without this being released. So everybody that's getting a forecast online or on TV or on the radio, it's all starting with these little boxes all across the world being released twice a day.
So it looks like it's made super lightweight, and because they are disposable, you don't get this back.
We used to get them back. That used to be the size of a lunchbox. I used to say, hey, this is harmless. There's a bag. Put it in the bag. Take it to the post office. We'll recondition it and fly it again. Oh, cool. But now we don't fly them again anymore.
It feels like it weighs maybe 3 ounces, 4 ounces. It's
really
super.
light.
It's pretty light. In this balloon will be lighter than air gas. We use hydrogen here, which is very flammable and explosive, so we have to be careful out there. We have it calculated to have enough hydrogen in this balloon to raise that, to lift that through its duration of its flight at 1,000 feet per minute. Based on time, we know how high it is above the Earth's surface.
And how quickly do you get the data back?
Instantaneously.
As it goes,
As it's going up, it's sending
I
data.
think a question a lot of people are going to want to know is, like, are there any risk to aircraft?
We have what's called a NOTAM, Notice to Airman. It's something that is filed for this site every day, twice a day. So there's a window where we say, we will be releasing one of these. So be on the watch out for a balloon with that attached and a parachute.
But by the time this thing gets up to like 35,000 feet, where the airliners
We're
are
above
cruising-
everybody's ceiling, right?
Well, I mean, at 35,000 feet, that's where the commercial airliners are cruising, right?
Yeah, but 35 minutes, we're above that, and no
Okay.
one's flying that high anymore. And so the whole rest of the flight, it's above all the commercial airlines.
Okay.
The probability of anything happening, I mean, is like, it's like a teaspoon in the ocean.
The likelihood of it coming into contact with an aircraft is super low.
Infinitesimally small, yeah.
Right. If it did, the weight of it, it's so lightweight, and it's foam. So when an aircraft hits it, it's okay.
Also, like the hydrogen, like I can't even imagine if a plane.
Oh, yeah. Poof.
Forgot about that part.
All right, so let's go get one of these in the air.
All right, out we go. What about this little tower right here that we're passing?
Well, you see up there, there's an anemometer, right? And a wind vane, an aero vane. So it's telling us the wind direction and wind speed up there. There's also temperature sensors. There's cameras that can see what we're doing right now. There's all kinds of meteorological instrumentation on that.
In this dish?
All the information that we get in our office, the model data, the satellite data, the radar data, the surface obs. So basically that's a link up to space with a satellite that we are receiving all the data that we use as forecasters to forecast. And when we create forecast and send out products, it goes out through that same dish.
Wow.
And then behind you, this is called the inflation shelter.
It almost looks like one of those things an observatory where you look at the stars.
We had a dish up there that would track this balloon, but now the dish is tracked by GPS, so there's no dish up there anymore.
Wow. Check out the size of this thing. When you put your ear next to it, you can kind of feel
Yeah, it sucks up the sound. This is a hydrogen-filled balloon. It's just latex rubber, right? Like a glove if you were doing surgery or something. Now, the amount of gas that's inside will stay constant the whole flight because it's tied off below. But as it goes higher and higher in the atmosphere, the atmospheric pressure gets less and less because there's less atmosphere as you get up. So now that balloon keeps expanding. So this will go up to about 100,000 feet to where it'll be as big as this building, seriously. And
really,
finally it'll get so thin there'll be a weak spot in the balloon and it'll pop.
Wow.
Attached to that is what we call a train. So you got string with a parachute.
Okay.
So when this thing pops, this thing will parachute back to the surface.
Wow.
This is the nozzle that supplies the gas from the room, the bottles in the room there, that net goes on here. It has to lift this weight. And when it lifts that weight up there, we know we have enough gas in there.
Oh, no kidding.
And then from the parachute is the rest of what we call the train, which is just basically string. That's going to go all the way out about 100 feet. Yeah, it has to be about 100 feet because we don't want any turbulence off of the balloon as it's going up to affect the pressure or anything on that radio song.
Even if it's super strong winds, one of these is going out.
Yes, no matter what. The only time we delay is if there's lightning. It's a safety issue for us, right? You ready to let this thing go up?
Yeah.
All right. Are you ready? You want to let Leo release it? There's not very much wind, so it'll be easy. Oh, this is Joe Biden. Made sure the balloon's getting up.
Why is it late?
Wasn't your balloon supposed to be up like 15 minutes ago? There are batteries inside here.
As soon as you unplug it, it basically goes on its own batteries and it's ready to go.
Yeah.
And when you take it off the plug, you must have to look at a screen and make sure they're talking before you pull it out.
Okay, the wind is coming from that way just a little bit. So we're going to have Travis stand here. There's my jet, by the way.
3 million new. I've looked into it.
Oh, is it 3 million?
Yeah, for a new one. But you can get a used one for like 1.9.
Yeah.
Not a big deal.
Grab the neck of the balloon, pull it off of that hook down below. Now walk it out this way. Keep coming out this way because the wind is coming this way. I don't want that to blow back into the building.
What's up, Leo?
And if you can, watch the string. And when the slack starts to go up, just do this with your hand.
You've never put a GoPro on it?
Never, not yet. Do you imagine what the picture would look like from 100,000 feet up?
In 3, 2, 1, let it go.
Lift your hand. There you go.
Oh, there's an airplane way up there.
So I have badly wanted to fly my paramotor around and be up there and record it coming up to me. I'm kind of nervous about it. You see how erratic it is? And that's on a good wind day. Did you see that? Did you see what it just did? So there's definitely some kind of shear up there.
You can see like the turbulence because you can watch this balloon go back and forth, so you can actually see the wind shear on the balloon. And actually, I've seen paramotor pilots on at least one occasion release a balloon just to see if it has that behavior.
We call those pi balls. We release those too. P-I-B-A-L.
Okay.
What we usually have is a theodolite. You look through it and you raise it. It gives you the elevation. You move it around. It gives you the azimuth. Yeah. And we used to track that to get winds.
Okay. So have you ever done that as a paramotor pilot though? Just gone out to the field? If you had any question, like release a balloon?
Well, my instructor here had Robinson. Every now and then he would release a pi ball. Okay. And we just sit there and watch. It's just a big red balloon, basically is all it is. He had a little party thing of helium that he got from Walmart. We'd fill it up. We'd just release it and just sit there and watch it for 10 minutes and see what it did. You
could do that with any balloon too, right?
Yeah, anything. Yeah, as long as you have some helium.
That's a good way because sometimes, the winds on the ground, like right now, they're very calm. And a lot of paramotor pilots might just come out to the field, not look at anything else and go, oh, the winds on the ground are calm, must be good. And then they get some really unexpected trashy air.
I will tell you as a meteorologist, right, that looks at the air in 3D, actually 4D, because I'm looking at time also, but I'm not looking at just the surface this way and that way. I'm also looking this way up, right? And then over time, that I can't tell you how many times, like when you're on the Facebook sites of paramotoring, people are talking about the surface, and I'm going to go send it because the surface is good. Yeah. And they don't even think to look above the surface. And I'm like, I can't tell you how many times I've gotten in the air where the surface is like this. I get up there and I immediately land because it sucks. Right?
So what are some tools that we can use? I know I use like RyanCarlton.com, and I use another app called PBG Report that gives me starting at 200 feet what the anticipated forecast winds are. Yeah. Are those good products, and how do they get to their data? Does it come from any of the stuff that you guys are doing with these balloons? Or
all of that is model data, and there's the global forecast system, there's the North American forecast, there's a European forecast, there's HRRR, which is high res rapid refresh, and there's RAP, which is rapid refresh also. I mean, there are tons of different weather models out there right now. And if you go to those places, you can select different models and look at those. And so you're actually looking at something that a human had no interaction in. It started with that balloon that we just released.
So that feeds the model.
That model got ingested, created these charts and these models. And like right now, we're getting winds as it goes up right now that we'll go see inside the building. So that will be observational data that's happening right now. So if I were to take my paramotor right now and take off and look at that before I did, I would know exactly what the winds are doing at every 100 feet up off the surface. And so I would know exactly what I'm flying into. The problem with like a lot of these places, they're just like at airport sites.
Yeah, it only shows you near an airport.
Right.
Correct.
So if you're nowhere near, well, weather changes very rapidly over space and time. And so what's happening 40 miles away probably isn't the same thing that's happening with you, especially in this area where we got mountains and stuff. Yeah. All the air is very influenced by topography, by the terrain, right? And so if you're in flat areas of the country, maybe you can look at something 30 miles away and feel pretty comfortable that that's pretty representative of what you're going to see when you're in the air. But here, that's not the case. And so you want to be looking at something that kind of tells you what's happening right where you're at. It'll cost you a little bit of money. My go-to is XC Skies. And it's for people that soar, balloons and paragliders, right? Not so much for PPG, but it's the same weather information. We're all flying in the same environment, in the same atmosphere. Yeah. And it has all the thermal stuff and all that, and you can choose to look at that or not. To me, it's like, am I gonna hit strong thermals or weak thermals as I'm flying, right? I'd rather hit weaker thermals than stronger thermals because they tend to upset me every now and then if I don't have my bump tolerance up, right? And I'm not expecting it. It's a 3D awesome view over time of what the wind's doing, and you pick the point. It'll be over your spot, and it looks at this model, and then you can change to the next model and change to the next model. And what you do is you build a consensus across the models and say, oh, you know, all the models say today's a good day.
XC Report or Ryan Carlton or Wind Alert, they all get their data from National Weather Service databases. Is that correct?
Yeah, so it doesn't matter which platform you go to, they're all pulling from the exact same data for that point. It's all point-based, right?
So they're like a data aggregator, essentially, but they're always using National Weather Service data.
We have the National Center for Environmental Prediction, that's NCEP. They produce all the modeling data, send it to us, and then we, as meteorologists and forecasters, come up with a forecast and stuff. You find what you get comfortable with, what works for you, that you find you have a history of, I can count on this kind of stuff. And stick with it. There's no really right or wrong, right?
Yeah, and it could be different for the area too. What I use in my local area in Florida might be a completely different model out here that's more accurate.
True. Yeah. Some models really have it nailed in this area, and other models have it nailed in another area, and it could be for a bunch of different reasons, right?
So it's probably a good idea to talk to local guys and figure out which models and which resources.
Right.
It's got a fancy stripe down the side. What was that?
Homeland Security.
Oh, Homeland Security, doing border stuff. Okay.
Border, yeah. Find something that works for you, get comfortable with it, that'll be your go-to, and that's what I've done with XC Skies. It's just something I've used for like over, I'd say 10 plus years, and every year I re-up my subscription because I'm so reliant on it. I've looked at it so much, I can get my go, no-go decision done in like 2 minutes.
In Florida, I use an app called Radar Scope, which pulls from your NextRad data. I think I pay $60, $70 a year for it. With the Pro version, I can get, I think, 60 frames of data versus 5 or 6 frames of data.
Right.
And so 60 frames of data gives you a much clearer picture. So for us, especially in Florida, we have these sea breezes that develop and come in.
Exactly.
And it's really cool because even though there's not precipitation within those breezes, just the change in relative humidity between that air and the air that's over Central Florida, it makes a line. Yeah. And you can see that.
Oh, I know it.
You can see it coming in, and it's been super helpful until I found that app to go, it can be beautiful, but you don't know there's basically a gust front. It's a sea breeze. It's 20 minutes out, and then everybody's like in a panic in the air.
Well, I mean, out here we get thunderstorm outflows, you get cold fronts, and then the sea breeze front that you're talking about. Those are all exactly the same thing. They're a density difference between two air masses, and the heavier, cooler, more wet air mass is pushing the other one.
Yeah.
You're going to get a wind shift. You're going to get turbulence in that. And so it's something you want to be on top of. Before I fly, I will be at my house, and I'll look at XC Skies or whatever I'm looking at, and I'll say, okay, today's a good day weather-wise. And then I'll look real quick on my radar scope, and I'll go, okay, storms are cool. I'm strapped in. I've got the motor on. I've got the wing behind me. And the last thing I do is I usually have my phone right here in the chest pouch. I pull it out one last time and go, okay, there's storms to the northwest. I've got about an hour before anything gets to me. So I go, okay, I'll fly for 40 minutes.
Now, I don't know if you know the answer to this, but some of these apps and models or apps, they only give you certain data if you pay for the app. Like I use Wind Alert, but I have the free version, so I only get the blend of the models. I can't look at GFS individually unless I pay for it. Same thing if I go to like a government website like Aviation Weather Center, and I'm looking at the radar data there. It's not that fine resolution where I can see like a gust front. I have to have the app. Why is some of that finer resolution isn't available for free through a government website? But it is available through a paid app.
They're making money off of us giving them data for free, which is fine. I mean, because the whole reason we exist, our what's the word I'm looking for? Our mission statement. Yes, our mission statement is protection of life and property. So all this data that we're getting from this balloon, all the forecasts, we give it to the general public, to the media, to anybody that can pass it on for free. We don't charge a dime for anything because it's all public information anyway, because we're a government agency. These private firms, they put a lot of time and money and effort into packaging all that information that we give them for free.
Right.
I mean, they got people they're paying, developers and all that kind of stuff. So they need money. And so they charge to package that and present it in a certain way that's pleasing, right?
And some of this stuff is really worth, like you just said, with the app that you use, it's worth paying for.
The government, the National Weather Service radar is just this real big, broad picture of the U.S. And you can zoom in, but you can't get a lot of high-res data with really good temporal resolution and stuff like that. So that's just based on the fact that it's so costly that we don't have it in the budget.
And your average taxpayer doesn't need that level of resolution.
Most people just need to know it's a storm coming, right?
Exactly.
For us, we need a higher level of meteorological information and services, right? So that's why sometimes you do have to go and pay. Anything that makes flying safer for me, I'm going to go for that.
Yeah, it's so worth it just to not get caught in one gust front, right?
See, I do a lot of fire weather information stuff, right? The three things that influence wildfires, it's the topography, the lay of the land, it's the fuels, what's burning, and it's the weather. I was trying to think of this the other day. We kind of have a triangle too. It's our skills, our equipment, and the weather. That's it. The weather is probably as important as anything that we need to know before we get up in the air.
You can show us on your system everything that's going to help people be safer.
All right.
What do you think so far?
I think this is super cool. And I've met Tom only on the phone before, but he's obviously like a wealth of information. And he's absolutely right. For paramotor pilots, I think that is a weak area. And I've seen it many, many, many times. And it's happened to me too, where we don't properly look at all the things that we should for the forecast and ground conditions, and then you get caught out in something really bad, or you get hurt. So,
right. Yeah, totally.
Good. Stay ready to roll.
Actually, Tom, that's how I've been for the last 6 months. I just did my first foot launch flight 3 nights ago.
What'd you do? What happened?
Pulled my meniscus or something in my knee launching, but I was so happy to foot launch my free ride 15 again on my motor the other night and not hurt myself.
You know what's weird for me? I kind of feel like it's like this Superman syndrome. Like all day long, it's like my knees are like killing me and I can barely get up and down.
Yeah.
But when I strap everything on and then I just go, it's like I don't feel anything.
That's the adrenaline.
Do you ever get that?
Yeah, absolutely. Like, just the other night, like right before I was like, I've got no pain in my knee. I'm going to do it.
Yeah.
And then, an hour after landing, pain came back.
Right.
So these have been updated, right, since 1988, I'm sure. Software, hardware.
Software and hardware improvements, of course. But the technology is Doppler technology. The Doppler effect is what you hear when you're at a train crossing in your car and the train is coming, and by law they have to blow their horn. So you hear the horn blowing as it's coming towards you, and then it continues blowing as it's going away. And you will hear the difference in the tone because the sound is coming at you versus the sound going away from you.
How does that sound?
How does it, Leo? How does a train sound when it's coming to you? The tone drops. And so that's what that's doing too. It's a dish that's 10 meters across. It's 30 feet that's in there. It's on a pedestal with a motor that's spinning it constantly, not stopping ever. It spins at this level, and then when it gets done 360, it goes up and it spins again. And so it creates kind of like a cake.
Oh, cool.
So a volume of the atmosphere all
That's
around
how you
here
get the
going out to
three-dimensional view.
200 miles away
Yeah.
in all directions. And so it's not just down low, it's way up high where the thunderstorms are. While it's doing that, it is shooting out super fast electromagnetic pulses. That electromagnetic pulse has a wavelength. And so when it hits a hydrometeor, which would be a raindrop or a piece of hail or something like that, it gets reflected back. And in between sending out those pulses, 1,000 a second, it has time to listen. Did that pulse get back to me? If it didn't, then there's nothing for it to hit. There's no rain, there's no hail. So if you're looking at a radar scope or whatever, there's not going to be any echo. It's going to be just a blank screen, right? But if it hits something and comes back, then it's going to paint a raindrop, a cloud, shower, whatever right there, right? And when it hits that drop, it can tell if that drop is moving away from the radar or towards the radar. That's the Doppler effect.
Okay.
So now it gives us velocity. Our old radars used to just give us echoes or returns of what it hit and the strength or how thick it was, right? But now it gives us all that plus the motion in the atmosphere.
That's how you get your tornado alerts?
Yeah, that's how we're seeing tornadoes.
Just based on the motion.
If it sees a piece of echo moving this way and a piece of echo right next to it moving this way, it sees that cyclonic rotation really small and it goes, well, that could be a tornado. So we actually get an alert. It's a vortex signature that says there may be a tornado right there. So then we look into it closer to see if we think that's a tornado.
So when I'm at home and I get a tornado warning, the system will give you guys an alert. You take a look at it, and then if it's verified, yeah, this is this. Then you issue a public alert.
Right.
At that point?
Yeah, then we issue the warning for it, right? The radar has all these algorithms, right? Up there is where it's collecting the data. It sends the data down into that building right there, and then that building sends it into this building. And along the way, we've got computers that look at all that data that radar's getting. And it has algorithms, and it paints the pictures, and it says, here's where the rain is, here where it's not, here's where the storm is, here's how strong it is, here's where it's moving this way versus this way, if it's rotating or not. And then it has these other algorithms that says, hey man, the hail in this storm could be up to 3 inches in size. And here's a spot where you may have rotation, that tornadic vortex signature. And so we get those and we say, is that really legit? Because, it's computer. It could be right or wrong.
Yeah.
And it could be contaminated by other kinds of data that thing is getting and be totally off base. And so that's where the meteorologist comes in with their expertise to say, you know what, that's real.
Yeah. It seems like AI is being used in a lot of different fields, medical fields now, to detect breast cancer and all kinds of things. Is that something that's even been thought about as far as National Weather Service forecasting goes, or is there any utility?
You asked a great question there, and the answer to that is absolutely. We're using AI in our forecast. We talked about, what do you look at before you go fly to see if it's safe? So you look at this model, this model, this model, this model on this application or that application, whatnot. So now what we're doing is we're looking at all the models together. We're smashing them all together, and each model will have 10 or 20 or 30 or 100 different iterations of the same model running at the same time, but they just tweak one little thing or another. And over time, it'll give you slightly different results for what the weather will be in day 2 or day 3 or day 4, right? Those are called ensembles. And for humans to look at that much data, it's hard, but AI can synthesize that information in an instant. Because a lot of it's pattern recognition.
That's what AI is it's detecting a pattern.
I know. That's what I'm saying. There'll be a day when AI, machine learning, all that stuff outperforms
Forecasters.
someone like me.
Yeah.
Within the agency, there is some angst. Is my job going to still be what I want it to be in 10 years? It is beneficial. I mean, we've used it long enough that we have statistics. We can prove how good or bad it is and how it performs and if it's better than what we can do as human forecasters. So the answer to that question is yes, AI will be used.
Do you guys still do pilot briefings here?
We used to, but no. For a long time, we had a sign on the door when you walk in that says we no longer do pilot weather briefings. That call this number, and it's the FAA. They do it.
You're right. The 1-800-WX brief.
Yeah, exactly.
Do it there.
Well, people are still here. Is Tim in the front doing something?
Wow. It's like a command center. It's nicer than any command center that I walked into as a military person for 23 years. It's fancy. What is the area of responsibility for your office?
See this line right here?
So it's a good part of southern New Mexico and part of southwest Texas.
South Central, Southwest New Mexico, and Far West Texas.
So all the way over to the Arizona border, huh?
Yep.
Is there always a meteorologist on duty?
There is never a moment that we're not open. 2 people sitting here in the operations area, monitoring weather, forecasting, looking at weather data, model data, all that kind of stuff. There's always 2 of us here.
I'm just asking questions that pop into my head. I think this is super cool, and I'm probably asking some non-pertinent paramotor questions because I'm curious.
It's been about 30 minutes. Where do you think that balloon is at right now? How high do you think it's
That balloon goes up 1,000 feet a minute. So it's at 30,000 feet, which is where a lot of commercial airliners are flying right now. So it's probably, they're dodging that balloon right now. They're going, oh God, what is that? Okay, so that weather balloon that we release, every couple of seconds, it's sending down a trace of the temperature in red, the moisture in green, and these winds. These are wind barbs. It's not just looking at weather at the surface. As it's moving up 100,000 feet away from the Earth's surface, it's sending down this information. And as a meteorologist, I can see that this is somewhat stable, unstable air. It becomes very stable, and then it's kind of neutral. And then I can see that we probably had some clouds right here just under 10,000 feet and very dry air above because this line is very far from that line. Pretty dry down south, but we did have clouds yesterday. Ignore the blue. This is the temperature of the air. Going this direction is warmer, going this direction is cooler, and going up is going up in the atmosphere. So the ground is right here. There's 10,000 feet, 18,000, 30,000 feet.
So normally temperature goes down as you go up, and that's
Right.
what we see here.
Right.
And then we see it inversion, and then it goes back to what we would expect
And check
until
this
you
out.
hit the stratosphere.
If we go to this morning, there's an inversion at the surface. Cold air settled at the surface. And
That's
so there's
this
an
morning,
inversion.
okay. That's pretty normal in the morning, right?
Yeah, especially here in the wintertime. But what's really more important is what's happening over here. Because as a paramotorist, what we really are concerned about is the winds. And so although these winds are kind of off the chart, these are showing us winds blowing from this direction to this direction, which would be an east wind. And then above that, you can see the winds all start moving this way, which means they went from east all the way to west. That's almost 180 degrees. Wind blows towards the point. It's like an arrow. You got the feathers at the end. And so it's blowing towards the tip. This wind would be from the west-southwest blowing towards the east-northeast. And each one of these feathers is 10 knots. So that would be 20 knots, which is close to 25 miles an hour. Down here, you have this one at the surface, which was northeast at 10 knots. So it'd be about 11 to 12 miles an hour. And then above that, it went east. And then up at this level, all of a sudden it turned and went west. So as a pilot, I would look at that and go, well, if I want to fly, I want to stay down here. I don't want to get into this area because this is where you got a sharp change in directions. There's going to be some rough air right there. But down here, it'll probably be okay because all these winds are the exact same direction.
Consistent.
You're looking for consistency. Look up here. See these solid flags? We call those flags. That's 50 knots. So that's 58 miles an hour plus 10. So that's like 70 mile per hour winds. But we're way up here at 30,000 feet. We're never going to be up.
Between each of these wind data points, what is the altitude change, or how fine does it capture?
It's plotting this information at both mandatory levels and significant levels. And so there's no definitive height above ground. It's a level. And it's based on pressure. So right now our pressure at the surface, 884 millibars. Then if I go up to 700 millibars, it will tell me that I'm 6,225 feet above the surface of the Earth here, which is about 10,000 feet above sea level. But this is all going way deep into the weeds, right? What is important is what you're seeing right here. This is a wealth of information. But when I'm looking at this as a paramotor pilot, I'm not looking at this as much as I'm looking at the winds. I will look to see if the air is super unstable. And super unstable would be this line really going really hard to the left.
Okay.
Because then I know there's going to be some strong thermals. I would know that would be a day that, you might get up there and get rocked a bit. It wouldn't be dangerous, but, it may not be the most comfortable, most fun flight. So I would know that. During the afternoon, the air mixes really well, right? Because you had sun on the ground's been heating the air's been going up and down and mixing, right? So in the afternoon, you get fairly uniform winds as you go up. But in the morning, you got that stable, heavy air, and it starts stratifying, making layers like a cake. And each one of those layers could have a different wind in it. But here, where we have stable mornings like I'm showing you here, the air tends to be not as fun to fly in because you fly in and out of different layers with different winds. And you can see it here. You got east and you got south and you got southeast and southwest, all within that same layer. And so as you're going up, it's a hard bump. You have to push yourself through that layer to get through that turbulence.
Then it gets stable.
Then you get into a smooth area, right? There's a layer that's smooth, but as soon as you get to the top of that, now you got another level of turbulence. Then you get into another smooth layer. We haven't even talked about rotor. Buildings and trees and stuff like that the air has to go over or through. Most of that stuff it can't go through. Air is less dense than a mountain, less dense than a building, so it's not going through it. It's going around it or over it, right? Yeah. And so if you can imagine, what I tell everybody when I teach weather classes is that air is a liquid, right? I mean, it's really a gas, right? But it behaves exactly like a liquid. we can see how liquid reacts to running into a rock in a river, right? We can actually see what happens as it's getting to that rock, and then when it goes past that rock. We can see exactly.
See the turbulence, yeah.
So as it's going to that rock, we can see it lift up over that rock. That's that. If we're doing ridge lift, if we're doing PG, and we're doing ridge lift, and you see the water going over that rock or that boulder, and that is exactly what we're doing when we're PG ridge soaring. We're just going back and forth, and we're staying in that wave that's going over the rock. But you look on the backside of that rock, and that water is just crashing, right? And turning over itself, and it's making a rotor, it's turbulent. So if you get blown back, that's why you say don't get blown back over the back of the mountain, because you get into that ugly air that will, anytime you get strong downward wind, vertical downward wind, that's going to collapse a non-rigid type wing, which is what we fly, right?
You were talking about stable air. And so where we're at in Florida, even in the wintertime, we get cold mornings down into the upper 30s, which is cold for us.
Right.
And it's really common when we have a northern air mass that comes over the state and we have those cool mornings that it's just dead calm as the sun comes up. Like there's zero wind on the ground, but at just 100 feet off the surface, it could be blowing 25.
Right.
What's going on there?
You've created two atmospheric layers. The layer that you're in at the ground, which is cold, at mid 30 degree, that is its own layer. And at the top of the inversion, what's above it doesn't come down, and what's below it doesn't go up. And so you're right. Down here in this inversion, you can have the lightest winds possible.
Yeah.
And then on top of that can be strong winds screaming across the top of that. It's like this is a lid.
Okay.
And until you heat the surface and break that lid, the air that's on top, which could be blowing at 20 miles an hour, will never touch the ground until it breaks. So you get to around 10, 11 o'clock in the morning.
Yeah.
You get enough sunshine, enough heating at the surface, those surface temperatures start going up. Now we'll start mixing what's happening above the inversion with what's happening below the inversion.
In those conditions, often we find we can get up, and it's actually a smooth transition above the lid.
Yeah.
And you get into that 20, 25 where you're just parked, and it's kind of cool
Oh,
because
yeah,
you just
yeah,
sit in
it's
one
fun,
spot and
yeah.
you look at everybody and you're
So it's
not
not-
moving at all.
You find it not bumpy to get into it?
Not at all if it's right after sunset. But as soon as the sun comes up, within just 25 minutes, that lid starts to break up.
Yeah.
And it starts to get very turbulent.
Oh, yeah, yeah.
In that transition. So you've got about 20 minutes to get
Right.
up there, play
get in
around,
it.
be parked, and get back down, because if you spend any more time than that, as that lid breaks up, it starts to get really rough trying to get back down.
And then don't you just wait it out for a while until it kind of fully mixes and then come down? Or do you just
No, I
have to come down through
get
it?
down before it starts to
Oh,
mix,
okay.
because otherwise
Because you could do
it's tough.
that. I mean, it's not.
Yeah.
I don't think it's dangerous by any means, as long as you're not starting to get super strong thermals. As a meteorologist, I always have a mental image of what the air is doing around me. So I think I'm at a disadvantage from a lot of people because I let it kind of get in my head and create demons. Like when I'm flying, when Anthony and I were flying, and all the other folks around here, they would go get up next to the mountains a lot quicker than I would.
Yeah.
Because I know what the air is doing there.
We hang back.
We were the hangbackers.
Tom and I don't go to the mountains. We don't mess with those.
I do go, but I'm like the last person
The
there.
conditions have to be,
But I have to wait and make sure everybody else is having a good time before I go.
because the concept of being able to see the wind freaks you
because I can
out.
see it. I can see it.
If you're going to fly the mountains,
see.
you can't see it, but you're looking at products that can tell you discreetly what those winds are up to a height that's at least a good amount above those mountains. Let's say the mountains are 6,000 feet and you're taking off at 4, and if the wind profile all the way up to 8,000 feet is showing less than 3 miles per hour and you're not in a thermic period, then maybe that's the day you can get a little close to the mountains, right?
You hope, in theory, I guess is the way to say
Time
it.
of day too, because you got the adiabatic, catabatic stuff.
Oh, yeah, you guys
Yeah,
got to deal with that
you
too.
You can look at this sounding, or you can go to like what I like to do, XC Skies, and I can pick a point right next to the mountain by where Anthony lives, and I can look at what does the wind look like this hour and next hour from there to well above the mountains. And that model will tell me something, another model will tell me something, but those mountains make their own weather, and the models can't resolve that.
Yeah.
And so you have to go sneak up on the mountain and say, is it like the model that I just looked at, or is it doing its own thing and it's not fun?
Because of the angle of the mountain when the sun hits it, you can't really detect the thermic activity really like you can with this. So there's all these variables, and that's why the mountains freak me out. And I will only go when the sun is, near sunset. It's not
Very
beaming
low,
on the mountain.
But here's the deal. Models don't model every single thing that's happening in the atmosphere, right? And so they struggle with the sun heating the earth and the earth heating the air and the air getting less dense and starting to rise, what we call thermal, right? They struggle with that. They struggle with turbulence. They struggle on very small scale resolution with complex terrain. They'll be really good in Kansas where it's flat for 100 miles.
Right.
They do pretty well. But then once you start introducing undulations in the flow, I mean, can you look at a river and put a rock in it and know exactly what the water is going to do after you put the rock in it? No. And the models can't do that either. So when you're trying to fly up against a mountain, it's always and it freaks me out when I'm on YouTube and I'm watching people do this.
These guys that do the X-Alps
Yeah. I'm like,
all day long.
well, for one thing, they
over
have
the
a whole
mountains.
lot more bump tolerance than I do, right?
Right.
They have a lot more trust in their equipment than I've ever developed.
All of this information that you're able to gather with all of this incredible technology, fixed-wing aircrafts, rotor-wing aircrafts are a lot more resilient to things than our fabric wings. So this is a tool rather than, what's that word?
Absolute.
Yeah, it's not an absolute.
I just came up with this the other day. I think there's a triangle for us. The
You got something about triangle.
Shut up, man. The three things that have the most influence on our safety is our equipment, our training and skill, and our decision making.
Yeah.
But then the third is the weather. I mean, there is nothing more important than those three things. I mean, those three things. If you tackle those three things and are on top of them, I think you fly safe your entire career.
No, I'd agree. I absolutely. And when you put in training and skill, I'd also put in mental state of mind on that given day, stress conditions, how
Right.
fatigued are you, have you eaten? There's all those things that kind of go into that one category.
Yeah.
And also just like risk, ability to manage and evaluate. And this is a huge part of being able to evaluate risk in our sport is understanding what's
Right.
going on with the weather.
You need to put time into finding a good source of information that's relevant to flying, right? So you don't need to look at all these models and all these soundings and stuff, although I do because I'm a meteorologist. But you need to find something that shows all the weather that's important, like the winds, the turbulence, and that kind of thing, and get comfortable with it to where it's something that you utilize before every flight. You need on your phone some kind of radar app, and you need to be able to look for and be able to identify outflow boundaries. And if they're coming towards you or away from you, and if they're anywhere near you, then that's a decision point that you use on whether to go or not go. It's really pretty simple. And once you get a flow about it and you be consistent, you can decide whether or not this morning or this afternoon is a good fly time in a matter of a couple minutes. I'll go, oh, crap, I think I could fly today. I'll run to my computer and look at things for 2 minutes, and then I'm either loading up or not. But then when you get out there, then you got to make another assessment.
Exactly.
Is this looking like what the model was telling me it should look like? And if it is, then you get up in the air. And then you make a third assessment. Am I still comfortable with the weather? And if not, there's no shame coming back around and landing and say, not today. The models aren't perfect.
There is no shame in landing out. If you get out there and let's say you're 10 miles from the LZ and the weather's changed and it starts to get really uncomfortable, then don't try and go back to the LZ.
Well, gentlemen, any closing thoughts?
There's this triangle thing. In another video, we'll spend some time with me showing you exactly how I look at the thing I look at to figure out if I think the winds, the turbulence, the stability, all that is good for me to fly.
Make sure that you like the video. This went beyond paramotor. I can't thank you enough, Mr. Bird.
My pleasure.
If you have any questions about the weather, make sure you leave it in the comments section. This is your chance. Thanks for watching. Try it again.
Okay, there you go.